All right, well, our next presenter is Dr. Douglas Shoemaker. He's the Director of Research and Outreach at UNC Charlotte's Center for Applied GIS Science. Every morning he wakes up and wonders how to thrive, not just survive. The Anthropocene, nice word. As co-author of the Futures...
Every morning I wake up and I wonder how to thrive, not just survive, the Anthropocene.
That's much better delivery. I apologize for my butchering of your excellent bio. That's right. All right. As co-author of the Futures Urban Growth Model, he has worked to establish an empirically based understanding of how cities evolve using a fusion of ecology, remote sensing, and demographics.
Thank you so much. And Derek, thanks for that great introduction to Under the Hood of the Futures Model. As an academic, I always love an opportunity to talk with practitioners. And I have to warn you that this presentation is sort of at the 40,000-foot level, but I hope there's a couple of take-homes there that you can incorporate into your own practice at some point. So futures really is like a crystal ball that will show us what's to be. And we love to take this tool, or I'm going to take this tool and use it as a lens to look at cities and the evolution of cities and what's going to happen. But like any mystic or fortune teller will tell you, if you want to get meaning out of what you see in the crystal ball, first you have to ask it a good question. So the futures on its own just shows you a landscape pattern. We need to ask it questions. Now, what the soothsayer won't tell you is how to assign meaning to that. So a lot of this story that you're going to see is about coupling the futures model with different ecosystem services model and econometric models to generate indicators that we can understand what these landscape patterns are going to mean. Oops. So the questions that emerge when you see these pictures from Derek's presentation about growth in Raleigh, you know, a bunch of questions come to mind. To me, it's what are some of the environmental and economic consequences involved with these trajectories of urban growth? So what is this going to mean in terms of the environment and land use? And is one growth pattern better than another, or can we improve on sprawl? You know, one of the great things about Ben's model, which is very accurate, but it sort of deterministically gives us a pattern that we're really used to. So what if through planning or being intentional, we could try to do things in another way? What would that look like, and what the heck would you do? And that's what this presentation is about, evaluating those things. Because believe it or not, we don't know. Marina Alberti's a noted urbanist. She says we don't know what the effects of different urban forms, densities, land use mixes, alternative infrastructures. We don't know, for example, how clustered versus dispersed and monocentric versus polycentric urban structures differentially affect ecological conditions. So we don't. And in this information vacuum where we don't know the consequences of these patterns, we routinely exchange nature's benefits, these ecosystem services, for economic growth, because that's something we can measure, right? And needed, I hope needed, are studies like mine that analyze the relationship between these urban patterns and ecosystem performance. So let's start off with a poster child for urban sprawl, Charlotte, North Carolina. It anchors the Charlanta mega region, which is the 47th largest economy in the world. My study area specifically includes 37 sub-watersheds, including Charlotte and just to the east of it. In 2006, where I start my analysis, it had about 1.1 million people. It's been growing rapidly. It's very interesting. It's got 46% urban canopy cover. So we get a long urban gradient where we have a lot of green near the city, but it kind of sprawls out in an interesting way. This gives us plenty of places to sample and figure out what's going on. And the region has also been the source of several ongoing studies through the Minnemeyer Lab. So we're getting to learn a lot about this area. So this is my study area, and this is my poster child for a sprawling pattern. Now, in Charlotte, from a starting point, we really see 5 different plausible ways that we could grow. Okay, now this is a U.S. sort of a model, so we could do nothing. We could just keep growing like we're growing. Keep jumping ahead. We could sprawl even more. You know, we could use development along highways and rural areas and sprawl even more with leapfrog development. Or we could infill. Maybe we could create rules and ordinances that force us to cluster our growth around existing infrastructure. We could entitle increased density. So we could zone things from R4 to R16. We could put more people on less land. Okay, we'll call that an increased density scenario. Put more on less land. Or, and this is probably the most likely scenario at this point, we could deregulate. And, you know, we could sort of cast it open and let people do what they want. We would anticipate this would increase per capita land consumption. Everybody would use more land, all right? So I wanted to test how these, I wanted to use a simulated environment to test how these different patterns would play out. And to apply meaning, I wanted to look at the domains of habitat. So what's it mean to critters? Pollution, non-point source pollution, and specifically how nitrogen and phosphorus influence water quality. We also wanted to look at climate and specifically carbon, thinking that if we keep more carbon on site and not in the atmosphere, it slows global climate change. And we also wanted to look at revenues, because as we grow out, the landscape value, the rents to landowners, the revenues that come with timber harvest landowners, they're going to change. Some will go up, some will go down. So to do this, to measure habitat, I intersected our patterns with a model called FragStats to measure fragmentation. And I used a model of vertebrate suitability from the Southeast Gap Project, which is a USGS initiative, and these are sort of my metrics for habitat quality. I used INVEST, different ecosystem there. That's a suite of ecosystem services models to get at what changes there would be across the landscape in non-point source nitrogen and phosphorus pollution, as well as what happened to the amount of carbon sequestered in each of these areas. And then to see what would happen with revenues, I borrowed some models from Lebowski et al. To sort of estimate what I thought those landscapes would be, what sorts of revenues they would generate in the future. And conceptually, I would use futures from a starting point in 2006 for the Charlotte area, and we would use the parameterization to create these different scenarios. And every time we do one of these, we flip a bunch of cells to develop type, and this represents a greenfield conversion. So futures only converts areas that are forest or farmland unimproved right now. And that's a greenfield diversion event. And when you do that, when you add the impervious surfaces, when you change the regime, you get a biophysical response. You get more runoff, you get more pollution in many cases. And that has an effect that we can use those models to quantify. Okay, so this represents a coupling of these land change models with ecosystem service models. And the great beauty of this is it allows us to get evidence about what might happen in the absence of measurable empiricism. So we'll never be able to conduct these tests in the real world, but we can do it in the simulated world. Okay? And then from the ecosystem service modeling domain, I get meaningful indicators, and we can actually assign some dollar values to those. So I'm going to jump right to my results, and I present these in the form of questions that people might ask about it. And we're going to start with the different domains that we measured. So this first series of slides are mainly, well, they're about fragmentation. I'll tell you right now, it's inconclusive. But it gives you a great opportunity to look at how realistically Futures puts in the development pattern instead of this bathtub model. So from our start, we have a fairly fragmented Charlotte region. And now here, red is new development, and black is existing development, and the greens are agriculture and forest types. So status quo is we just grow into the futures. This is a 2030 depiction with the patterns that we've been doing, and it looks like that, and the fragmentation is about similar. Here's sprawl. You can see that, and again, in all these cases, the same amount of population is coming to the area. It's just how it's patterned, how it's distributed. And sprawl probably has the worst fragmentation, but we can see the patterning. There's the infill scenario. We can see how futures will cluster new development around existing infrastructure. Here's our increased land consumption. Increased density. So this is, we put more on less land, and it looks fairly compact. Oh, I'm sorry, that's wrong. So this is the increased land consumption. Everybody uses more land. Believe it or not, the Charlotte areas, each person is using almost a third of an acre of land, and if you count office space, retail space, roadways. And here's our increased density. So we put more people on less land. Again, the fragmentation, it's pretty severe throughout, so that's sort of inconclusive. So how does habitat change? So here, these are maps of the region, and they represent 4 different habitat types and how critters avoid urban areas. So these dark browns are places that for birds like forest interior birds or salamanders are not tolerant of humans, all the way up to bright yellow places where those might be for pigeons or coyotes, things that get along great in urban situations. So when we do these different scenarios, specifically if we look at habitats for intolerant woodland species, right? What the colors mean here is red is we lose land as compared to the status quo condition, just leaving it alone. We do worse than leaving it alone. And green is we do better than leaving it alone. So you can see right off the bat that, probably the best one for saving these sensitive areas is an infill scenario, and the worst one is sprawl, all right? And so what we think this might mean is that if you were a land manager assigned with promoting woodland creatures, you might like an infill scenario best. Okay, let's look at which of these landscape patterns exports the least amount of nitrogen non-point source pollution. And here, blue is water. There's purple things where they don't change, across the 25-year time span. And we go from a low of very small to a high of 26 kilograms per hectare over the time space. And again, we see a flip-flopping of patterns between sprawl. It looks like sprawl in urban areas, that Charlotte, does better than just leaving the system alone, and infilling in urban areas does worse. And it flips when you get to the rural areas. Of course, the one that seems to do best is the increase the density scenario. We're putting more people and more things on less land. So the state publishes some prices for what nitrogen pollution costs, and when I did this research last year, it was set at $43.85 a kilogram. And if we work that out, the 24 years discounted at a rate of 4%, these are the kinds of avoided costs costs that you would incur if you had to treat all that non-point source pollution. So the increased density is the cheapest. It saves us the most money, and the deregulate scenario costs us the most, but infill is close. It's a fairly expensive scenario when it comes to nitrogen, and sprawl looks pretty good there. Sprawl is actually our next best model. So that's counterintuitive and interesting. So we do the same thing for phosphorus, the same sort of modelings. We've seen the same footflat patterns between sprawl and infill, between rural and urban areas, and we also come up with the increased density scenarios being the best, better than leaving the system alone. And again, these are all costs, are all negatives. The cheapest is the increased density. The most expensive is to deregulate. Infill is surprisingly expensive. It generates a lot of pollution, and sprawl is surprisingly good. Okay, carbon. So we're interested in carbon. The more carbon that we keep in trees and soil, the less is in the atmosphere. There's been a lot of talk about carbon trading schemes. So it's an interesting thing to look at. And here we look at carbon sequestration. We have our start, and things that are orange are places that have lost carbon as compared to 2006. So this in our area is most associated with cutting down trees, okay? And places with the purple trending to blue are places where there's has the most carbon over this time period. And those are places where essentially the forests have been left alone and they've been sequestering carbon for 24 years. When we look at the different scenarios, we see a really similar pattern. Flip-flopping between urban and rural areas, although infill it seems to be across the board bad. Our winner, once again, is more stuff on less land. These are all costs, losses of carbon. If you look to the literature, the social cost of carbon is, if I pick a median point, it's about $60 a metric ton. And if we work that out over 24 years and discount at 4%, we end up with these numbers. Our cheapest scenario, it's still a cost, but our cheapest scenario is increasing density. Our most expensive is infill. So infill patterns, which kind of mirrors a lot of what Derek's group found in Western Carolina with farmlands. Infill patterns consume a lot of carbon, and sprawl looks surprisingly good. So this is sort of interesting. Most of us environmental types don't really consider revenues, but I think it's fascinating. So when we awarded different, based on records, we can award a different amount of revenues based on land cover types. The least expensive are pasture types, which generate something like $23 a year. The most expensive ones are urban types, which can generate $1,000 per hectare a year or more. And so when we run those types out over time, we get these maps. The dark green represents $12,000 per hectare per year. Light green goes as low as $65 per hectare per year. Reminder, a hectare is about 2.5 acres, I think. So which of these landscapes made their landowners the most amount of money? Increasing density. By putting more people and more businesses on less land, this is needs to be borne out, but that's a conclusion we might have guessed at. The deregulate, of course, sprawling, spreading things out, the landscape generates the least amount of money. Okay, so let's summarize our findings. So if we tally up the cost of environmental services, the scenario that cost, now they're all costs, but the ones that was the least expensive was increasing density, and the one that was most expensive was the infill scenario. And it's a virtual tie with the deregulate scenario. So when we compare, let's see if what the landscapes made with their new patterns versus what those environmental costs are, the increased revenues dwarf what the environmental costs are. So which tells you a little bit about how we value things here in the U.S. So if we if we subtracted the environmental costs from the extra money that we made with land cover types, we would get a plot that looked like this, and we might say that, hey, you know, the increased density, it made a lot of money and it had relatively few costs, so this is the winner in terms of dollars, right? But if we overlaid something that we can't value easily, like habitat for salamanders, you might be tempted to try the infill scenario, because the infill scenario made pretty good money that dwarfed its environmental costs, and it saved the most habitat for forest interior or things that didn't like urban landscapes. So the role of configuration. Now, in all these scenarios, we're putting, it's the same number of people coming in using the same amount of land. The only thing is different is where you put it. Do you let it sprawl or do you cluster it? And just by doing that, so essentially we're taking away, you know, instead of doing this on the back of an envelope and saying we have this many people coming in so we're going to get this answer, right? We actually play it out with futures and we see where it gets put that matters. We see really, really, really different patterns. And typically, and if you want to go back, the paper should that hopefully it'll be out this year, we see it flip-flopping between urban and more rural watersheds. So we get, you know, place matters. So that leads me to a couple of take-homes. Take-home number one is spatial thinking is needed. These are non-linear relationships. So where you put things in the relationship to other land cover types and on a slope, what's high, what's low, and how close are you to stream networks, it matters, right? In aggregate, it matters. So that's different. That might be, I mean, I think it's something we've all suspected, but I've got some, you know, some testing that shows that's true. Two, abandon one-size-all thinking whenever possible. If you come in with a rule that applies to countryside and cities evenly, maybe in some, what I believe might be a misguided desire to be more equitable, you get really different results that are probably maybe counter of what the result you were trying to achieve was. So I hope this gives you courage to go and say, our place is different, let's do it right for us and our situation. And the third piece is embrace density. The only story that is consistently clear and easy to take home is that when you put more stuff on less land, you get better outcomes. And this is, if you're an urban planner, this makes a lot of sense. If you're the public, it doesn't. In many cases, the public thinks that the most benign landscape is a low-density residential, you know, big houses with tons of green in between them and long driveways, right? And I think that we unequivocally show in this scenario analyses that if you get people to put more on less land, they'll make more money and we'll have less damage to the environment in terms of things like pollution. We'll slow our use of carbon and we'll save more habitat for sensitive critters. I think that's it.